Have you ever, walked into a really massive building or maybe driven over a huge bridge and just stopped for a second and thought, how how does this thing actually stand up?
Yeah, how does it take all that weight, all those forces, day in, day out without, well, falling down?
Exactly. It kind of makes you look at everyday stuff a bit differently, doesn't it? When you start thinking about the engineering behind it all.
It really does.
Today, we're going to pull back the curtain a little on that engineering magic. Welcome, everyone, to a deep dive.
Yeah.
We're focusing on the world of structural design.
Specifically, we're looking at two, let's call them unsung heroes, beams and shafts. You see them everywhere, but maybe don't always notice them.
Right. And our mission today is really to dig into some detailed engineering textbook excerpts we've been looking at.
Yeah, we want to pull out the really key nuggets of knowledge, help you understand the core ideas behind how these critical parts work.
Think of it like getting the inside scoop on the silent calculations holding things together.
That's a good way to put it. Our source material is pretty solid. It's from a foundational textbook on mechanics of materials.
So it gives a really clear fundamental look at how engineers design these things for, well, both strength and efficiency.
And hopefully by the end of this, you'll have a much better grasp of what engineers are thinking about. You know, everything from just resisting loads to making sure they're not wasting material.
We're aiming to turn these maybe complex-sounding concepts into something, well, accessible and interesting. Give you a real feel for the engineering all around us.
Definitely.
Okay, so let's dive in. Beams first. I mean, when you think about a building, what's holding up the roof? The floors.
Beams, almost always beams, they're absolutely fundamental structural members doing the heavy lifting in pretty much every building you go into.
And the main idea behind designing them is
Zucker.
strength, right?
Exactly. It's all about strength. A beam has to be able to resist the internal forces that build up inside it when you put loads on it.
Those forces being shear and moment.
Precisely. Shear is the force trying to sort of slice it across its depth, and moment is the bending force trying to curve it.
Gotcha.
And engineers use basic tools, like the shear formula and the flexure formula, to calculate this stuff. They generally assume the material is, homogeneous and behaves in a linear elastic way.
Like a spring that bounces back perfectly.
Pretty much, yeah. That simplifies the math considerably.
Okay, so we've mentioned bending stress, stretching one side, squashing the other, and shear stress, the slicing force. Those are the big ones for beams.
They are the primary concerns, yes. But there's another one, sometimes overlooked, a localized compressive stress.
Compressive, meaning squashing. Where does that happen?
Right underneath where a load is applied directly. Like imagine a heavy column sitting right on top of a beam. There's a concentrated squashing force right there.
Ah, okay. Is that a major problem?
Well, usually it diminishes pretty quickly as you move away from the load point. It's often small compared to the main bending stress.
But engineers still deal with it.
Oh, absolutely. They use something called bearing plates. Think of them as like little steel pads placed under the load.
To spread the force out.
Exactly. Spreads the load over a wider area of the beam, reducing that intense local squashing. It's like putting a coaster under a heavy mug to protect the table. Protects the beam from getting crushed locally.
Makes sense. So it's not just about resisting stress inside the beam, is it? What else can go wrong even if it's technically strong enough?
That's a really important point. Strength isn't the whole story. Stability is huge.
Stability.
Yeah, imagine a long, skinny ruler. You can press down on the thin edge, and it's strong that way. But if you press down on the flat side...
It buckles sideways easily.
Right, that's kind of like sidesway buckling in a beam. If it's not properly braced along its length, it can just sort of flop over sideways, even if it can handle the downward load. So bracing is critical.
Okay, so stability. Anything else?
Deflection, how much it sags.
Right. Even if it doesn't break, you don't want it bending too much.
Especially if it's supporting something brittle, like, say, a plaster ceiling. Even a tiny sag in the beam above could cause ugly cracks in the ceiling below. So sometimes the design is governed by how much it deflects, not just its strength.
Interesting. Okay, now, how does the type of material change things? You mentioned brittle materials earlier, like concrete.
Right, and this is where things get particularly interesting for brittle materials. Unlike steel, which might bend or stretch a lot before it breaks.
The brittle stuff just snaps.
Pretty much, especially in tension when it's being pulled apart. Concrete is strong in compression, being squashed but weak in tension.
So for concrete beams, you really need to know where those pulling forces are.
Absolutely critical. You need to understand how the principal stress, that's the maximum pulling or pushing stress at any point, regardless of direction, how that changes throughout the beam. Because failure will likely start where the tensile stress is highest.
You mentioned the source shows these stress trajectories. Sounds complicated.
It sounds abstract, but it's actually a really neat visual concept. Think of drawing lines through the beam that follow the direction of these principal stresses.
Like a map of the internal forces.
Exactly like a map. Solid lines usually show the direction of the main pulling forces, tension, and dashed lines show the main pushing forces, compression.
And there are patterns to these lines.
Oh yeah. They always cross the beam's neutral axis, that imaginary line down the middle, with no bending stress at a 45-degree angle, and the tension lines and compression lines always cross each other at 90 degrees.
Okay, cool pattern, but what's the practical use?
Immense practical use. Knowing these directions tells engineers exactly where to put reinforcement, like steel rebar in a concrete beam.
Ah, you put the steel where the concrete is being pulled apart because steel is strong in tension.
Precisely. The steel takes the tension, the concrete takes the compression. These stress trajectories guide the placement of that reinforcement to make the brittle material work effectively. It's how we build strong concrete structures.
That is clever.
Yeah.
Okay, so that's brittle materials needing careful mapping. But most beams we see are probably steel, right? Which is ductile.
Correct. Steel, wood, many common beam materials are ductile, and for these, thankfully, you usually don't need to plot those complex stress trajectories.
So what's the approach then?
It's more about making sure the actual stresses, the bending stress and the shear stress, stay below certain allowable limits.
Limits set by building codes.
Exactly. Design codes provide these limits based on the material and safety factors. It's like a speed limit for stress. As long as you stay below it, you're generally okay.
Now, for longer beams, you said bending is usually the main concern.
Mm-hmm.
And there's a special property involved.
Yes, the section modulus, usually written as S.
Section modulus. What does it tell you?
Think of it as, a measure of the beam's shape efficiency in resisting bending. It combines the beam's cross-sectional geometry, its size and shape, into a single number.
So a bigger S means it's better at handling bending.
That's exactly it. A higher section modulus means it can resist a larger bending moment for the same amount of stress. Engineers figure out the maximum bending moment the beam will see. They know the allowable stress for the material.
And they calculate the S they need.
Right. The required S is just the maximum moment divided by the allowable stress. Then they need to pick a beam shape that has at least that much S.
Simple enough. What about the beam's own weight? Does that matter?
Sometimes. Often it's small compared to the loads it carries, so it might be ignored for an initial calculation. But if you do include it, you just need to make sure the S you choose is a little bit bigger than the calculation initially suggests to account for that extra weight.
And how do they pick the actual beam if it's a simple shape, like a square or a rectangle?
For simple shapes, yeah, you can sometimes calculate the required dimensions directly, but for standard steel shapes, like those W shapes,
Wide flange beams.
right, engineers use standardized tables. Think of a huge catalog published by organizations like the AISC, the American Institute of Steel Construction.
So they just look up a beam in the catalog that has the required S or more.
Pretty much. And there's usually an economic angle, too.
Cost.
Always cost. Among all the beams in the table that meet the required S, engineers will often pick the one with the smallest cross-sectional area.
Because less area means less material?
Less weight, and therefore usually less cost. Assuming, of course, that the chosen beam doesn't deflect too much.
Okay, so you pick a beam based on S for bending. Are you done then?
Not quite. Crucial second step, check the shear strength.
Back to the slicing force.
Yep. You've selected the beam based on bending, and now you have to calculate the maximum shear stress it will experience and make sure that is also below the allowable shear stress limit.
Is this often a problem?
For long, slender beams, shear is often not the controlling factor. Bending usually governs, but for shorter, deeper beams, especially ones carrying heavy concentrated loads near their supports, shear can absolutely be the critical thing.
So a beam could be fine for bending but fail in shear.
Definitely. The textbook actually has a great example of that. They pick a beam size based on the bending moment. It looks good, but then they run the shear check, and whoops, it fails.
So they had to pick a bigger beam.
They had to go back and select a different section, one that could handle the shear, even if it was maybe over-designed for bending. Shows you got to check both.
Good point. Okay, let's talk specifics. Steel beams you mentioned, rolled shapes.
Right. They're formed by passing hot steel through rollers to get specific shapes. That W460 by 68 you mentioned earlier?
W for wide flange, 460 millimeter deep, 68 kilograms per meter.
You got it. And those wide flange shapes are super efficient for bending. Why? Because most of the material is concentrated in the top and bottom flanges, far away from the neutral axis.
Where it does the most good resisting bending.
Exactly. It maximizes that section modulus S for a given amount of material.
And you mentioned stiffeners sometimes.
Yeah, sometimes, especially near supports where the shear force is high, the thin vertical part of the beam, the web, or even the flanges might be prone to localized buckling or crippling.
Like crumpling under the load.
Sort of, yeah. So engineers might add vertical plates, called stiffeners, welded to the web. They act like little reinforcing ribs to prevent that localized failure. You often see them on bridge girders.
Okay. Now shifting to wood. Typically rectangular, you said?
Usually, yeah. Easier to mill, cut, and connect. But the key thing with wood, especially for anyone doing DIY or even pro construction,
Is the difference between nominal and actual size.
bingo. You buy a 2x4 or metrically maybe a 50 by 100 millimeter. That's the nominal size.
But it's not actually that big.
Nope. After it's milled smooth, the actual or dressed size is smaller. That 50 by 100 might actually be closer to 38 by 89 millimeter, or in the US, a 2x4 is actually 1.5 by 3.5 inches.
And for calculations.
You must use the smaller actual dimensions. If you use the nominal size, you'll overestimate the beam's strength and stiffness. Could be dangerous.
That's a really crucial practical tip. Okay, so what if a standard steel shape or a single piece of lumber just isn't big enough for the job? Huge loads, really long spans.
Good question. That's when engineers turn to built-up sections.
Building beams out of smaller pieces.
Essentially, yes, customizing beams. For steel, you might see massive plate girders on bridges. These are made by welding or bolting thick steel plates together to form the flanges and the web. You can make them much deeper and stronger than standard rolled shapes.
And for wood.
You might see things like wooden box beams, literally beams built like a hollow box, or very commonly now, glulam beams. Glue laminated timber. They take smaller boards, like maybe 2x4s or 2x6s, and glue them together under pressure to form one massive beam. You can create really large, strong, and often quite beautiful architectural beams this way.
Wow. But if you're joining pieces together, doesn't how you join them matter a lot?
Absolutely critical. For any built-up section, you don't just check the overall bending and shear stresses in the beam. You also have to check the stress in the fasteners, the welds, the glue, the bolts, the nails.
To make sure they can handle the shear flow between the parts.
Exactly. You need to ensure the fasteners are strong enough and spaced correctly to make all the individual pieces act together as one single solid unit. If the connections fail, the whole beam fails.
Is that related to the example you mentioned about nail spacing?
Yes. The textbook example showed how in a built-up wooden beam, the nails holding it together needed to be spaced closer together in areas where the internal shear force was high.
So more stitching where the stress is greatest.
Precisely. More nails per foot or meter to handle that higher shear flow and keep the parts from sliding relative to each other. It ensures the beam behaves as designed.
Okay, this is all about making beams strong enough. But you mentioned efficiency earlier.
Right, and that constant drive for efficiency, for using material wisely, leads us to a really interesting concept.
Which is?
Well, think about a standard beam, one with the same cross-section all the way along what we call a prismatic beam.
Okay.
Now, the bending moment inside that beam usually changes along its length, right? It's often maximum near the middle or at the supports and less elsewhere. So, if you design the beam's cross-section to handle the maximum moment, what does that mean for all the other parts of the beam where the moment is lower?
They're stronger than they need to be.
Exactly. They're only fully stressed, working at their maximum allowable capacity right at that one point of maximum moment. Everywhere else, there's extra material, extra weight, extra cost, just sitting there, not working to its full potential.
That sounds inefficient.
It often is. Which brings us to fully stressed beams, or sometimes called non-prismatic beams.
Non-prismatic meaning not the same shape all the way along.
Correct. These are beams cleverly designed with a variable cross-section. The shape changes along the length,
Why?
so that the bending stress reaches the maximum allowable value at every cross-section, or at least close to it.
So you're making all the material work hard, not just the material at one spot.
That's the core idea. You're fully utilizing the material's strength everywhere. The big benefit.
Less materials.
Less material, which means less weight, and usually significant cost savings. The textbook shows pictures like bridge piers that taper elegantly.
Getting thinner where the load is less.
Right, or beams under floors that might be deeper in the middle where bending is highest. It's about putting the material only where it's needed.
Where do we see these in the real world?
They're quite common in mesh parts, actually, because variable shapes can often be easily cast or machined. In structures, you might see concrete beams that are deeper near the supports. They're called haunched beams.
I think I've seen those under bridges.
Very likely. Or sometimes with steel beams, instead of changing the whole beam shape, they'll weld extra plates, or cover plates, onto the top and bottom flanges only in the areas of high bending moment.
Beefing it up just where needed.
Exactly, adding strength locally.
Now, the source mentioned a really cool example, something about leaf springs.
Ah, yes. This is a fantastic real-world connection. It turns out that the ideal shape variation for a fully stressed beam under certain common loading conditions, like a simple beam with a load in the middle, often involves a parabolic change in depth.
Okay, parabolic shape.
So think about leaf springs on a heavy truck or a train car.
Those stacks of curved metal strips.
Yes. They're essentially acting like a beam designed on this fully stressed principle. The stack of leaves, each slightly shorter than the one below it, approximates that ideal parabolic shape change.
No way. So the reason leaf springs work so well is because they're basically a form of non-prismatic, fully stressed beam.
That's a major part of their design genius. It allows them to support heavy loads efficiently and provide suspension using this principle of varying the stiffness along the length. It's a really clever application.
That is brilliant. Okay, but designing these variable shape beams must be harder, right?
It is more complex than designing simple prismatic beams. The standard flexure formula we use for prismatic beams only gives an approximate idea of the shape needed for a non-prismatic beam, especially if the taper or change in shape is gradual.
Are there catches?
There's a key one the source points out. In a tapered beam, the absolute maximum stress might not actually occur where the bending moment is highest.
Right, how?
Because the changing cross-section itself can introduce stress concentrations. So the stress might actually peak somewhere else, even if the bending force is lower there. The calculation gets tricky.
So it's a powerful concept for efficiency, but needs careful, maybe more advanced analysis?
Definitely. The simple formulas give a starting point, but for accurate design, especially with significant tapers, engineers often rely on more sophisticated methods, like computer simulations, finite element analysis. There are small errors in the approximate methods.
Got it. Okay, let's shift gears from beams to shafts.
Right. Shafts. Think rotating components.
Like axles in cars,
What?
drive shafts in machinery.
Exactly. They're typically circular in cross-section, though not always. And the key difference from beams we've been discussing,
They twist.
they resist torsion twisting loads in addition to bending loads, like beams do. And because they often rotate, they're frequently subjected to cyclic stresses, which brings fatigue into play. That's a huge factor in shaft design, making sure they don't fail over time from repeated loading.
So bending and twisting. How do engineers handle that combination? It sounds complicated.
It is a bit more involved. First, they have to figure out all the forces acting on the shaft, usually from things like gears or pulleys attached to it.
Okay.
They resolve these forces into components acting in different planes, usually two perpendicular planes, say vertical and horizontal.
Like looking at the forces from the top and from the side separately?
Kind of, yeah. Then they draw separate bending moment diagrams for the loads in each of those planes, just like they would for a beam.
So two bending diagrams.
Right. But then comes the clever part. They combine these two bending moments at any point along the shaft using vector addition, like finding the hypotenuse of a right triangle, to get a single resultant bending moment.
The overall bending effect at that point.
Exactly. And in addition to that, they also draw a torque diagram, which shows how the internal twisting moment, or torque, varies along the shaft's length.
Okay, so you've got a map of the combined bending moment and a map of the torque all along the shaft. What next?
Next, you identify the critical sections. These are the points along the shaft where the combination of that resultant bending moment, M, and the torque, T, is likely to cause the most severe stress state.
Where it's working the hardest, basically.
Pretty much.
Yeah.
Now, at these critical points, where does the stress actually occur? The maximum bending stress happens on the outer surface of the shaft.
Makes sense. Furthest from the neutral axis.
And the maximum shear stress from the torsion also occurs on that same outer surface.
So the outer surface gets hit with both maximum bending and maximum twisting shear.
Yes. Interestingly, the shear stress caused by the transverse forces themselves, like the shear force V in a beam, is usually much smaller in shafts compared to the torsional shear and bending stress, so it's often neglected in basic shaft design to keep things a bit simpler.
Okay, so you have combined bending stress and torsional shear stress acting on the same points. How do you know if that's too much? It's not just one stress type.
Exactly. This is where theories of failure come in, because the material is experiencing both normal stress from bending and shear stress from torsion, simultaneously what engineers call a state of plane stress. You can't just compare each one individually to an allowable limit.
You need a way to judge the combined effect.
Precisely. Theories of failure provide criteria based on the material properties to predict when failure might occur under these combined stress states. It's like having a special rule book for multi-stress situations.
What's a common theory used for shafts?
For shafts made of ductile materials, like most steel shafts, the maximum shear stress theory is very commonly used.
Maximum shear stress theory. What does it say?
In simple terms, it states that failure, yielding, occurs when the absolute maximum shear stress at any point reaches the shear stress that would cause the material to yield in a simple tension test. It relates the combined effect of bending and torsion back to a fundamental material property.
And this leads to actual design equations.
Yes, applying this theory leads to specific equations that relate the required shaft radius or diameter to the resultant bending moment, M, the torque, T, and the material's allowable shear stress. The textbook shows an equation like this.
So you plug in your calculated M and T, the material's allowable stress, and solve for the size needed.
Essentially, yes. But remember, M and T vary along the shaft.
Oh, right. So you might need to check multiple critical sections.
Absolutely. You might need to apply this calculation at several points along the shaft, wherever M is high, wherever T is high, or wherever both are significantly large to find the location that requires the largest diameter. That largest required diameter then governs the design for that section, or potentially the whole shaft for simplicity.
It really highlights the level of detail needed. It's not just one calculation.
Not at all. It's often an iterative process of analysis and checking at multiple points to ensure the entire component is safe and reliable.
Wow. Okay, so just like that, we've kind of journeyed through the design thinking behind beams and shafts
Yeah, from basic strength to stability, deflection, material choices.
to efficiency with those clever non-prismatic beams and then combining bending and twisting in shafts. It's
Yeah.
amazing how much goes into these components we see or don't see every day.
It really is. Concepts like the section modulus, that bending scorecard, become really important.
And understanding the big difference in designing for brittle versus ductile materials, mapping those stresses,
Or the ingenuity behind fully stressed designs, like those leaf springs.
it definitely makes you appreciate the engineering.
Hopefully. So maybe the next time you walk across a floor or see a big truck rumbling past.
You'll think about the beams holding up that floor or the axle shafts on that truck.
Exactly. Take a second to consider all the silent, unseen calculations, the careful design choices that went into making sure those parts do their jobs safely and efficiently.
It's a pretty profound thought, isn't it? What other hidden design complexities might be shaping the everyday objects all around us, just quietly making things work?
That's the question to ponder. We really hope this deep dive encourages you to look at the engineered world with, perhaps, some new eyes, appreciating the blend of science, maths, and practical ingenuity that holds it all together.